So we technically did unit 5 before unit 4. They're both polynomials. Unit 4, so we're kind of going backwards if you're looking on Math Nation, still polynomials. Now we're going to get more into the nitty gritty of graphing them. Okay, so today we're going to classify them in a by factored form. Tomorrow and Wednesday, we're going to talk about some theorems that are going to help us when it comes to graphing. We're going to do a quick little quiz on just these 3 sections on Friday. And then next week, we'll start graphing. Okay, so we're going to use what we're doing this week to then apply to the graphs. Okay, a lot of this is Algebra 1 today, with, of course, a nice little Algebra 2 twist. So remember, a polynomial is a finite, let's get this pen working, there we go, is a finite sum of monomials, which means it does not go on forever, right? There is an end. Sum of monomials, terms in which all variables are raised to non-negative integer powers, and there are no variables that will appear in the denominator. So we are going to have monomials, so different terms put together. Okay, their exponents will always be positive exponents with the integers, so no fractions. And then we're not going to have any variables in denominators. Okay, if any of that happens, then it's not a polynomial and we have to fix it. So based off of that, I want you to try to determine, we can do a couple first. Are they polynomial expressions? If we say no, we need to fix it so it is. Okay, so first one, 3x squared plus 2y plus 4. We have 3 pieces. Are my exponents whole numbers that are positive numbers? Do I have anything in a denominator? No, so guess what? This is good, we like this one. Do you like the next one? No, because what's wrong with it? The 1/2 as a exponent. Okay, so what could it be instead? What if it was 8a to the power of just 2? That would work. Plus 2c. That would be a polynomial. That would be fine. Okay. This one is 5r plus s divided by t. So you can rewrite this as 5r plus s over t. Do we like this one? We do not like this one. How come? There's a variable in the denominator. So how could we rewrite this? Ooh, that was hard to say. Sure. If they were multiplied together, that would be fine. 5r plus st. That would work. So you try 4, 5, and 6. Say yes or no. If you say no, change it so it works. All right, Brandon, number 4, yes or no?
Yes.
Yes. It is good to go. Pick a number 1 through 30, please.
1.
Muriel, number 5, yes or no? Ooh, it tricked you. How come? It has a negative. It's really small. So to fix it, though, what could we do? Yeah, if it was 9x to the positive 3, then that would be fine. Good. All right, Muriel, pick another number 1 through 30. 10. Brandon. Back to you, friend.
I said no.
How come? Why not? Does it have an exponent that's negative?
No.
Does it have an exponent that's a fraction?
No.
Does it have a denominator with a variable?
No.
So guess what?
It is.
It's fine. Yep. So numbers that are constants are good to go. All right, so now that we know what a polynomial is and what it's allowed to contain, now we're going to name them. Who remembers the name if it's only one term or one piece? It's going to be something nomial. It was in the description earlier. Monomial, yeah. A monomial means one term. What do you think 2 terms are? There you go. And 3 terms? Good. Anything bigger than 3, we're just going to call a polynomial. Like that. Okay. When we classify them, we have 2 parts. So part 1 is doing the how many terms. Part 2 is going to also be the degree of the polynomial. Okay. The degree comes from our highest exponent, or the term with the highest power. Okay. So if my degree is 0, who thinks I know what that name is? I kind of said it for number 6. It's a constant. Yes. Like, so that's technically 5x to the power of 0. Anything to the power of 0, though, is just 1, right? So it's just a number by itself. So that's what a degree of 0 would look like, is just a number. All right, what's it called if it's, I almost said it. If it has a degree of 1. Like, what if I had something that looks like this? What? Linear, yes, linear. The number 1 is a line. Fun fact. Okay, and that's in the form of mx plus b, right? Which makes a line. So if your degree is 1, it is a linear function. What if our degree is 2? Looks like this. What's it called? Come on, kids. Quadratic, yes. I remember this because you have 2 quad muscles in your legs. You got 2 quads. All right, how about a degree of 3? What? Cubic, yes. Okay. So this would be a cubic function. Or if I had 2 pieces, if I had like x squared y1, that would technically be a cubic function because you would add your exponents together. Okay, so if there's a single variable with the highest exponent, or the term if you add them together if that's the highest, that gives you the degree of the entire polynomial. Yep, because it's in the same term. Yeah, you do the degree of the term, the piece. Yeah. All right, number 4. You have 4 of these in $1. Quarters, yeah, this is called a quartic. So if you had an x to the power of 4, or if you had something, let's see here, if I had 5x, if I had something like this, 5x cubed y plus 2z, even if this z had a power of 3 to it, the degree of this would be 4, because 3 plus 1, that term has a degree of 4. That would be the leading degree of the entire thing. And 5. What happens if you have 5 babies at one time, besides cry? What is it? Quintuplets? Yeah, so this is going to be called a quintic if you have 5. So x to the power of 5, okay? Or if your term has a degree to the power of 5, it's called a quintic, okay? There used to be a show on TLC called Outdaughtered. If you ever watched that, the mom had 5 girls all at once. They had a little show. I mean, it happened. Yep. She was the first one where it was all 5 girls and they all survived. So, okay, so we have some examples, okay, of polynomials. They are polynomials. We're going to figure out how many terms they have, what's that name, what's the degree of the function, and what's the name for that. Okay, so our very first one, I'm going to do like 2 of them, I think, and then I think I'm going to let you do the rest. My first one, 3x to the 5th. How many pieces are there? There's 1 piece. So what's that called? A monomial. These should always have nomial in them. Ooh, nomial. That's a weird looking A. Okay. What's the degree of this function? What's my highest exponent? A 5. So what's that called? A quintic. So it's technically called a quintic monomial. 8r squared plus 4r plus 7. How many pieces? What's that? Do you have a question? If it's over 5? What do you mean? Oh, we're not going to go a degree above 5. They have names. We're just not going to do it. Yeah. Well, because we said what to do if there was more than 3 pieces. We call it a polynomial. Degrees higher than 5, they have names. We're just not going to use them. Okay, 8r squared plus 4r plus 7. How many pieces? What is it? How many pieces we got? There are 3 pieces. So what's that called? There you go. What's our degree? A 2. So that's called a, you got 2 of them in your legs, a quadratic. I'll do one more with you. How about that? How many pieces does the number 7 have? 1. What's that called? Okay. What's our degree? 0. That's called a constant. All right. I'm going to stop. You're going to keep going. Talk to each other. Fill in the rest of this table. All right. Check your answers with mine. 3x squared plus 2y squared. You should have said was a binomial and a quadratic. A plus 2a cubed plus a squared plus 4. That's 4 pieces, so it's a polynomial. It is a cubic. What's happening is it is not written in standard form. If I were to rewrite this in standard form, 2a cubed should come first, right? And then a squared, and then a, and then 4, right? Okay. When that happens, this is called your leading term. That typically gives you your degree as well, okay? 6x plus y to the 4th, that's going to be a binomial. There's 2 pieces, and y has the highest exponent here, which is 4, so it's going to be called a quartic. Is that one in standard form? Technically, yes. Alphabetical order, x should come before y. And then 2x plus 3z is a binomial, and our highest exponent is a 1, so it's linear. All right. Whoop. We did not have to combine any like terms with any of these problems. I believe on your homework, some of them are not in standard form, or they're not, simplified. So I think there's one with parentheses. Make sure you do distribute that out so you have 3, 4, however many clear pieces, and then you can judge it from there. Okay, so you're going to have to combine like terms if possible. Okay. What kind of polynomials have we been dealing with in this class? Like what, do any of those words look familiar to you? Yeah, we've done lots of stuff with quadratics. We've done lots of stuff with linears. Good. Quadratics, linears, lots of cube roots or cubes. Yeah. So a lot of this should look familiar to you. We've been working with it a lot. Okay. All that factoring stuff applied to quadratics and cubics. Usually a linear was what we divided by or something like that. So we've been doing a lot of degrees of 1, 2, and 3. Okay. Our exponential functions, are they polynomials? An exponential would look like this. Is that considered a polynomial? No. How come? What's in the exponent? The issue is that there's a variable in the exponent. So it's a function, but it's not a polynomial. Okay? So let's do an always, sometimes, never kind of thing. A monomial. Is that going to always, sometimes, or never be a polynomial? Only one term, yeah. So they're all polynomials. We don't give it a special name if it's more than 3. Yeah. Okay, so yeah, I would say this one is sometimes, because if you play the what if game, what if that one monomial has a negative exponent, right? So it really depends on your exponents. How about a polynomial? Is a polynomial always a monomial, or sometimes or never? Sometimes. If it's the number 5, or even 5x, that's a polynomial that is a monomial, right? But if I had 5x, whoops, go ahead. If I had 5x minus 3, that's a polynomial, but that's not a monomial, right? There's 2 pieces. All right. A quadratic function is blank a polynomial function. A quadratic function. What's a quadratic function? It has an exponent of what? So is that going to work for me? Yes, always. Because we're going to have an exponent of 2. Good. Okay, so now we're going to kind of prove some things, okay? We're going to go into polynomial identities. Oh, come on. There we. Why is this happening? Come on, draw. What's happening? All right, so a polynomial identity is a true equation that is generalized, so it can apply to multiple situations. Based on this definition, we can infer that both expressions are always equal, no matter what number replaces the variables. You can replace it with anything and it's going to stay true. Okay? So the first identity it wants us to do is show that a plus b squared equals a squared plus 2ab plus b squared. So how would I show my work? There you go. I would actually write out a plus b times a plus b. We would multiply this through. So a times a is a squared. A times b is ab. B times a is also ab. And b times b is b squared. This is not really anything new. It's just we're kind of giving it a name. Okay, this is called a polynomial identity. We are proving that these two polynomials are equal to each other. I could plug in a 1 for an a and 2 for a b in the entire equation on both sides, and they should equal the exact same thing because both expressions are equal to each other. Okay. So how could I show the identity for part A, for 2x plus 1 squared? What expression is equal to that? We're going to have to write it out twice again. 2x plus 1, 2x plus 1. And FOIL like we did above, 2x times 2x. There is 4x squared. 2x times 1 is 2x. 1 times 2x is 2x. 1 times 1 is 1. Bring these together. So what is our polynomial identity to 2x plus 1 squared? 4x squared plus 4x plus 1. Again, not really new math. It's just a new question, a new way to identify it. They're called polynomial identities. All right, how about part B? Can you try? Yes? I want you to try. Try part B. All right. When you are ready, check your answer. Look at the TV. You should get 9x to the 4th plus 6x squared y cubed plus y to the power of 6. Yes, sir.
So why wouldn't you add the exponents of both variables?
Because they're different variables.
Okay.
Yep. You do that to find the degree of the term. Like the degree of the middle term is 5.
Okay.
Right? But to simplify the polynomial, you keep them separated. Yeah. Good question. Anybody need to see it, or are we okay? We're good? All right, we got to remember some factoring because it's definitely going to come back to play. Difference of two squares. Who remembers how we did that? What was its polynomial identity? We have two things being subtracted from each other, perfect squares. We were able to do the square root of each, one being added, one being subtracted, right? That's the polynomial identity. Perfect square trinomials came from either adding or subtracting the same thing to each other and squaring it. So that's what we did for number 1. We did that for here, we did it for A, and technically we did it for B. Those are called perfect square trinomials. So writing them out would be in a polynomial identity. Sum of cubes and difference of cubes. Remember SOAP? Yes, no, maybe? We got to remember these things, guys. I told you they were coming back. SOAP means same, opposite, always positive, right? So here we have the same sign, opposite, always positive. And for difference of cubes, we're going to subtract them. Opposite, always positive. Same, opposite, always positive. So we went off of the plus here, same, opposite, always positive. We went off of the minus. And everyone's favorite, the quadratic formula. I know, it's here. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So when we were doing all these things, these are technically polynomial identities. It's the same expression being rewritten. All right. So when it comes to proving something, I'm going to prove the next one, number 2. Prove x plus y times x squared minus xy plus y squared equals x cubed plus y cubed. So we're proving which one of our factoring methods? Almost. Sum of cubes, right? It wants me to prove that this is the sum of cubes because of that plus sign. So it wants me to prove that they're going to be equal to each other. Okay. How am I going to prove it? We're going to actually do the multiplying. Okay. If I multiply those two together, does it simplify to just x cubed plus y cubed? All right. Let's see. X times x squared is x cubed. I'll make this bigger for y'all. There we go. X times negative xy is negative x squared y. X times y squared is going to be positive xy squared. Then we're going to distribute the y. Y times x squared is x squared y. Y times negative xy is going to be negative xy squared. And then y times y squared is positive y cubed. Now, how on earth am I going to use that to prove that it should just be x cubed plus y cubed? Yeah, they end up canceling. Which ones end up canceling? Yeah, negative x squared y, positive x squared y. And then look, xy squared minus xy squared. So after all of that, we're left with only x cubed plus y cubed. So that's using our factoring methods to prove that they are equal to each other. All right. You want to do like one more, and then I'll let you work on the assignment while you're in here? Okay, let's do one more. Let's do this top one, because they're all pretty closely related to each other. Let's do 98 c to the 5th d minus 50 c d to the 7th. Which one do you think they're trying to prove? Difference of, it might be squares, it might be cubes. We see the minus, we know it's difference, right? Right now, 98 and 50, 5, 7, those aren't squares or cubes. What could we do to simplify this maybe a little bit more? Yeah, find the greatest common factor. What can we divide out of 98 and negative 50? 2, yeah. We can divide them both by 2. Can we take anything else out? How about C's? Can I take any C's out of both? How many? Just 1. Can I take any D's out of them? How many? Just 1. All right. So if we do that, 2CD, 98 divided by 2 is going to be 49. C5 divided by C is C4. D divided by D is 1, so it's gone. All right, 50 divided by 2 is going to be minus 25. C divided by C is 1. I'm not going to put multiply by 1. D7 over D gives me D6. Okay, so we weren't sure if it was going to be difference of squares or just blah, blah, blah. Difference of squares or difference of cubes. Which one does it end up being? Squares. How do you know? 49 and 25, big ol' hint. And what about the exponents? They are also, they're even numbers. Yep, they can be divisible by 2. So both of those prove it's a difference of squares. So using what we've done, so we know 2CD just hangs out here, right? Difference of squares, I get to add and subtract the exact same thing. Add and subtract. How do I know what to put in? Yeah, they're square roots. What's the square root of 49? What's the square root of C to the 4th? C squared, good. What is the square root of 25? And what is the square root of D to the 6th? D3, good job. Good. And we're done, that's as low as it's gonna go. That's a polynomial identity. So it's just another word for saying factor again, sorry. I told you it was coming back though. It just has a new word. Yes, we have to do it again because we have to remember because we got to use them again. Okay, so I'll stop here in the notes. I want to give you time to work on the worksheet so you can ask me questions if you have them. That top little chart you're naming, make sure you simplify if you can. If you need room to show work, your back is blank. And then work on the rest. All right, let me know if you got questions.